Well, welcome to the Bartlett Together Festival 2021. If you've joined this session, this is the Prototyping for Change, Persuasion through Making talk. This session is being recorded and it's going to be added to the faculty YouTube channel, the Bartlett Together website, and it's going to be forwarded to you as an attendee if you've registered. Through the Zoom interface, we do encourage you to submit any questions that you might have to the speaker, that'll be me, at any point during the lecture using the Q&A function at the bottom of the screen. You can submit your own question or you can upvote the questions that other attendees have submitted. The presentations due to last approximately 50 minutes or so, and we'll have the Q&A session at the end, and we'll be aiming to end the session at 15:30 hours local London time. So this is the opening talk for the Bartlett Together Festival this year, and we know that for some of you it will be your first week at the Bartlett, so welcome, welcome, welcome. Good morning, good afternoon, and good evening, depending upon what time zone you might be in if you're streaming from across the world. My name's Christopher Leung. I'm an academic at the Bartlett. I major in technology and environmental design. I teach a studio here in the Masters of Science in Architectural Computation, and I have a research interest in the information and process challenges of bringing industrialized manufacturing to construction. I just wanted to start by reiterating the Dean's message to you that the Bartlett wants to build a better future, and we've listened, and we have the 12-point action plan to go forward with this. There are a huge number of challenges to do this, and this talk is, I hope, and at least a provocation for some of the ways that this might be done. I'm going to try and offer a context through which to understand this presentation. It has two parts. The first is environmental and the second is economic. And I think that without both in lockstep, many of our aspirations might not be realizable. I thought I'd start with this image. It's the Earthrise image from the Apollo missions in the 1960s, and it's a very stark reminder that the Earth is one planet. From space, there are no national borders visible. But our actions as a species have now become so large scale that we can see them from space, and indeed they do span across those arbitrarily drawn national borders. The Earth's also a very varied place climatically, and there isn't and never has really been a one-size-fits-all structure that you can make as a habitat. There has nearly always needed to be some degree of localization. And the reality is that the predictions for how the climate might change over the next 20 to 50 years suggest that that localization really is under significant threat. I'm always reminded of Buckminster Fuller's writings in the 1960s and 70s, where he reminds us that we are actually astronauts. We happen to be journeying on spaceship Earth, and our relationship with the cosmos and the relationship with our macro meso environment is very much influenced by that dynamic that we have as we go around the sun. Wherever you may stand on nuclear energy, we do have to acknowledge that we do have access to a naturally occurring thermonuclear reactor. Luckily, it's 7.5 light minutes away, and something that I think we should make more use of. The amount of solar energy that's received on landmass across the Earth is in the order of 25,400 terawatts on average. This is a phenomenal amount of abundant free energy, if we could only find ways to usefully convert a small fraction of it, we could meet many of our demands. The second lens that I want to offer is economic. And back in the day when I was a student at the Bartlett some 20 plus years ago, these two reports were highly influential, and they were essentially the UK government trying to understand what was wrong with the construction industry. And one of them was more about the relationship that clients have with getting buildings built by consultants, and the other was an analysis of the way that construction worked overall. And in both cases, the news wasn't great. The construction industry is very fragmented. Its structure is particularly difficult to rationalize and make efficient, but they did make a whole series of recommendations, and amongst them was standardization, ideas of interchangeability, and generally looking towards industrialized manufacturing to address some of its shortcomings. That red line is when the reports were written, and the analysis of construction's productivity over that time, roughly up until the present, doesn't look like terribly good reading. So the blue line basically shows that construction in real terms has pretty much stayed the same, if not a little worse. If you compare that against pretty much all other forms of industrialized manufacture and just industry generally, it's fared very badly. Analysts have also looked at levels of digitization across industrial activities. And if you look at advanced manufacturing, which is cars, aerospace, defense, and even basic goods, white goods, freezers, toasters, the comparison with construction is jarring. We come second from the bottom, but at least we're just above agriculture and hunting. And it doesn't take much observation to suggest that this might be one of the problems. The point of production in construction is generally a mess, a bit like this one, even if it's a really well-managed mess. Most of the rest of industrialized activity has moved into factories and undertaken some level of automation, maybe not quite as much as Tesla, but always tending towards trying to streamline processes and basically adopt principles of industrialized manufacturing. So I'm going to take a risk here, and in preparing for this talk, I wanted to choose what I thought was the most impactful bit of manufacturing innovation that I could think of. And I came up with this. So this is from the 1960s, early 1960s. It's a diagram by a NASA engineer that shows the dual NOR input logic gate. It's implemented in this diagram as resistors and transistors. I show this really as a representation because it's one instance of something that's a computer scientist would call functionally complete, meaning that you can use it as a building block to build all of the other 16 logic gates, so AND and NAND and so on. Point of showing this is that at the time, early 1960s, there was really no way of trying to make this very, very small, very, very efficient and cost effective. And it came down to a few engineers who were working at Fairchild Semiconductors in the early 1960s to literally take a piece of graph paper and try and figure out how would you dope a piece of silicon with N and P junctions in layers to make one of those dual 3-input NOR gates. And this is literally the same bit of graph paper that anyone in a high school would use for any kind of representation. The point being that, like all manufacturing, one of the obstacles was to find the right form of representation. And this is a photo micrograph of one of those very early production integrated circuits. The process that's used is photolithography, and essentially that graph paper drawing was turned pretty much directly into photomask and then photomicrographically projected to make it very small. The graph paper is about 400 times larger than the chip. And I never failed to be amazed, collecting lots of these chips over the years since, that if that innovation hadn't been made to basically get from the graph paper to a photo mask to something that you could project onto the piece of silicon to then dope with the chemistry, it's very hard to imagine how you would have been able to achieve the guidance, navigation, and control, which is basically what was necessary to get the chips to be small enough, to have low enough power, and to be reliable enough, and also to be able to scale so that you'd be able to put enough of them to make an embedded computer, which is what the Apollo guidance system relied on. Now, I point this out because Apollo is seen as a technical achievement, but it also ought to be seen as an organizational management and systems engineering achievement to develop the manufacturing necessary to deliver it. Sorry, just checking. So fast forward quite a long time, disruptive processes and tools that we have access to today. So perhaps one of the most democratizing has been that desktop 3D printing, rapid prototyping allows us to make to get rapid feedback from making physical parts in all of their forms, whether it's subtractive or additive. And so this is a very small selection of the extensive making facilities that are available at the Bartlett and indeed in UCL more widely. So this is just a photograph showing the tool room, milling machines and mill turn machine that's located at Here East, as well as one example out of the many utility industrial robotic arms. As well as just to point out that instrumentation for measurement is almost as important as facilities to make, and I'll mention some more of that later. And really just to point out that test and instrumentation facilities are a really important part of anything to do with making. And another part of those disruptive processes has been the democratization of access to software to model in 3D and to model mechanisms, to be able to have direct lines to simulation, as well as being able to script and code generative software from scratch without needing dependencies on lots of proprietary software. I make the point of one-to-one because we experience buildings full scale when we touch them, indeed when we're touched by construction. And I would advocate that we need to cultivate our thinking about the making of things, not the modeling of things. And I think that full-scale prototyping, which is really what all of the rest of this talk tries to show examples of, directly engages with both the technological means for making, individual processes of making parts, assembling those parts and turning them into constructions, as well as the information requirements to get to that point. And I think the two are intimately linked. I have to declare that I've always adopted an approach which is component based, and this is not to everyone's sort of tendencies. Some architects go from form and then components come from forms, but I think I started studying architecture at a time when it was still fashionable maybe to think about buildings that are essentially made of parts, and that those parts have got relationships to the adjacencies, and it's really collections of parts that build constructions. This may be a somewhat old-fashioned view, and it's also an approach that I think has been fed by a certain type of drawing, where the drawing's not so much a instruction as an attempt to negotiate the difference between what you want something to be and your understanding, and it's one that tends to evolve, of your means to make that idea a reality. So this is an example from a fairly famous building in Paris from the late 1980s, Parc de la Villette, part of the external wall cladding. And just to make the point that industrialized manufacturing has been here before, for housing, for example. So this is the Lustron house, which was basically a kind of kit build system. This is from 1955. And just to say that industrialized manufacturing has been deployed, particularly for housing, in the past. It's not a new idea. There is a certain tension that it's often not treated as architecture. It's merely construction. It certainly had its place. So the main bulk of this course, after having tried to establish a context, is really about making things. And if I were allowed to make one assertion, it's this: we all have ideas, often very good ideas, and these are really the easiest things to do. Making our ideas can and usually is very hard, but the argument made here is that that's what makes the difference, and what makes those ideas become worthwhile. It also forces us to question our assumptions and usually have to discard a lot of comfortable and habitual modes of work. And I think the rest of this talk's trying to focus on the capability of making things and the kind of challenges that it provokes. So I'd say that the act of making things is a catalyst for thinking about how things might be made, because your cognitive models always being questioned by you actually trying to make things, whether they're partially manually by models or in a computer. And it's always very satisfying to see students that you've been involved with teaching go out into the professional world and start to apply some of the principles and develop their own language. So this is a student from 2 years ago who followed the Design for Manufacture program and has been making bespoke objects ever since. I wanted to touch on basically a series of projects just to try to illustrate different approaches to this, that there's always this search for a language through the drawings, and then search for suitable media to try to investigate the feasibility of making the drawing. So this is a connector component that was designed to be cast in the first instance. And just to say, during COVID, all manner of improvisation was tried to be able to do casting. And this is actually one that we made right in the middle of the pandemic, which was a sandcast light alloy aluminium version of the connector. This is one that was made pre-pandemic under more favorable conditions, really just to make the point that casting gives you a really efficient near net shape in a way which subtractive processes would produce a lot of waste from. And what's really interesting about making castings, especially of functional parts, is that you can make them to surprisingly high tolerances, and really the post-casting work that you do can be designed to be very minimal, making them material efficient. This is a project by a member of the workshop staff over at Heeries, Melis van der Berg. And it's a study really just to show moving from the world of scanning an object and producing manufacturing information from it. The processes that you go through to make all of the tooling for it, the process of casting itself, and an examination of the quality of the result. And really just to say that casting just as one process to present in a talk like this, it is iterative. So there are many process variables in going from that idea, the type of alloy that you choose, the exact melt temperature that it's poured at, the type of sand, how compacted the sand is, and all of those variables, they play into the outcome, and it is very much a dialogue that you're cultivating between the idea of what you want, which might started out being a simulacra, if you like, of a pebble, and the achievable result. And a lot of that dialogue is provoking exactly how sensitive the process really is to those process variables. Casting has been something that's been explored over the last year and a half as a material using aluminium, which has got a very low melting point, but also because it's relatively easy to machine post casting. So it's proven to be quite an effective material to composite with other materials. So this is some further work by students, again following the Design for Manufacture course, where they've looked at ways of using, for example, generative design to, through topology optimization, minimize the amount of material while having no detriment to the load transfer capabilities of the part's geometry. And those of you who perhaps are familiar with the Renzo Piano and Richard Rogers IBM traveling pavilion from, I think, the early 1980s might recognize the fingers that were explored in this casting as an introductory exercise. And just to say that whilst traditionally you might have used a timber mold pattern, using things like 3D printing makes this process very iterative, and the whole assembly can be made as a single print. And this is one of the examples that students cast this year on the Design for Manufacture program. And this just as a slide to suggest how all of these parts might go together. So this is a part that was designed, again, did use generative design for topology optimization, does show how different materialities can be connected in a fastenerless way. Just wanted to pick out another project, again, trying to get from a simple representation of an idea, in this case, the idea of leaves that have nastic responses to their environment, and objects that you might make to explore the physical manufacture of that phenomena. So this happens to be made out of aluminium as well, and a series of machined parts that became a project that was investigating the relationship between a made object that we called a survey probe and the environment that it was placed in. It's a passively activated device. It relies on solar gains to actuate a wax charge, and the wax changes its phase when it's heated, and when the thermal energy is rejected back to the environment, it freezes and changes its reverses its state. And just a short animation to show over a diurnal cycle the response that the device had to being heated during the day and then slowly cooling in the afternoon. Really, again, just to say that verification of a design does involve the almost design for measurement in the idea of the design. So the original sketch that started this project's development was just a leaf folded out, a leaf that's been touched that folds up, and creating a link between design intent and the way that an object behaves, and trying to verify it almost needs you to put markers in the scene, think about how an object will actually be measured and monitored in situ. And often as architects, it's something we often never get to do with full size buildings, although I'll show some examples later on. where there's almost a design for metrology built into the design of the object's making. Not everything is about heat that you can gain. I started off by saying that there was a huge amount of thermal energy available from the sun, and that could be converted to electricity through photovoltaics. There's also a source at nighttime under clear skies for cooling, something that I think is very much underused. And we've been experimenting again, trying to just use all of the palette of available rapid prototyping means, 3D printing, turning, CNC work, electronics, to make sensors that would monitor that cooling in a low cost, low part count way. And we've been experimenting with cooling panels that would effectively reject heat to the night sky, and potentially constructions that might go onto buildings or onto the roofs of buildings to investigate this, and possibly add a dimension to the fifth facade of the building that was a heat rejection rather than a heat gain. And these are some studies of the sorts of assemblies that we've been looking at. And again, just utilizing that palette of rapid prototyping facilities that are available to make example parts. At every stage in this, there's always looking over one's shoulder at the past and seeing that everything that that might be an example that you could choose or try to adopt and adapt nearly always has a hidden detail in it. And I think that part of the curiosity of taking a component-led or component-level-led approach to design and making is that you're always trying to understand how things work through dismantling them, and trying to, as it were, reimagine how parts actually function. And this was a study that was done over 2 summers and was turned into a skills exercise for one of the courses, which was essentially looking at a scissor mechanism for controlling solar blinds, and going through a process of by part, by individual component, into assemblies, into instructions for making using these different processes, and accounting for the near mechanical tolerances that are involved in making something like this. And again, reaching into the chest of, or toolbox rather, both digitally and in terms of manufacture, to marshal all these things together. So that's an example of one running. I really want to move forward to examples of student projects which have taken this much further and also tried to deal with this at more at the scale of buildings. So this is an example again from the Design for Manufacture program from Cristina La Sierra from 3 years ago now, that looked at incremental sheet forming, which is essentially using a single point to form metal. And the opportunity here is that every single panel can be different, because you're essentially leveraging that it's easy to change a computer program and you effectively get variety for free, which suggests a surface that might evolve with different structural requirements in a very cost-effective way. This is actually her end of year show 3 years ago. Here's another project which deals with forming and the relationship between geometric precision and imprecision of making in a different way. This is a project called Sloppy Topologies and Precise Datums, which simply used a hydroformed process which is somewhat unpredictable, and then project precision just using a mapping between geometry of the made object being extracted using a technique called photogrammetry to get measurement data, and then projecting precision back through the motion of a robot to cut apart. And this is the same exercise done at a larger scale, just to suggest what this might be in terms of a manufacturing process and the kinds of potential it unlocks. Other projects that have been done looked at reciprocal structures in timber, and thinking about how you might make fastenerless structures by tessellating these. Again, dipping into that palette of manufacturing processes, in this case, 5-axis robotic milling. And again, always wanting to reach out to the public by putting these projects on show, just getting feedback, engaging acceptance. And just to say that these projects do follow the students out into the professional world. So this is one of the students who graduated, who went to work for a design for manufacture company and took all of those principles that they learned, taking the as-built information from the environment as a 3D point cloud, making drawings directly from them, developing models that were adapted to the realities of an existing building and not making presumptions about a pure idealized form. This is just a project to say that mechanisms that might start as a simple idea of just looking at how heat gets absorbed by a building and how heat might get rejected was turned into a project where the articulation of essentially a passive flow of energy was used to change the performance of the fabric. So this is essentially thinking about variable performance of facades that are completely passively controlled because of their exposure to thermal energy and their loss of thermal energy. Again, this is done at full size, everything is one-to-one, always thinking about how the material reality gets coupled to the flows of energy that go through it and how you might use that to marshal its behavior. And it can happen at a very small scale. This is a project that was dealing with how material geometry and chemistry and interaction with water retention and nutrient availability might lead to bioreceptivity, particularly on materials that were porous, mapped, and it had adjacencies to materials that were non-porous. This was a study that was carried out 6 years ago at Bartlett, which was looking at how cementitious concrete that wasn't ordinary Portland cement, was bonded with magnesium phosphate, might be bioreceptive and become favorable to colonization by microalgae and microflora. Again, always going that step of trying to make the objects at full size, expose them to a testing environment, instrument them so that you understood how much exposure that they had and how it varied over time and what the results were, and trying to get a data set that's contributing to an understanding of actually how materials behave rather than how you might idealize or that a mathematical model might idealize they do. You might be wondering where all of this can be done. And as I've said, I've just made a very limited selection of examples of making processes that are available. And I'd really point you in two directions. One is to the workshop facilities at the Here East Manufacturing Centre over in Stratford, and the other at 22 Gordon Street in Bloomsbury. Almost all of these activities, I think bar one, were done in either of these locations. And also online, for those of you who haven't yet made it to campus, there is an extensive connected learning portal provided by the workshop, which looks at many of these processes from laser cutting to all the way up to dealing with robotics. It's been said that as a species, we've been perhaps the most impactful in the history of the Earth, but it might also be said that we're arguably one of the most resourceful species that have ever been on Earth. And I certainly think that you're got to be the most digitally capable generation of students in history. So this gives the world a lot of reasons for optimism. And anything that you do while you're at the Bartlett is really investing in your own futures. And those two challenges, the environmental and the economic, I think should be addressed together by trying to understand as in a way that's been attempted, I think, back in the 1950s and 60s of thinking through how we might adopt principles from industrialized manufacturing into construction. I think it's a challenge that we've got to address, but I would say that I think it's an organizational innovation, not just a technological innovation, which we need to come up with. And I think that if if I were to leave you with one challenge, it's that you need to calibrate the impact of your ideas in the digital realm with prototyping in the physical realm. And I think you need to do this because that's really where you'll get the feedback, and also where you'll be able to make things which demonstrate your ideas. And I think that's the way to win persuasion. I try hard to walk my own talk. And this last slide here is and contains some examples of my small contributions to addressing those challenges ahead. Thank you very much. I think that's that was the 50 minutes. So if I open this up to Q&As, if there are any. Just looking over at the chat window. Right, Noor Mubashir. As architects, we don't often. So, first question up here. As architects, we often don't explore many options in materials and its applications. How important is it for an architect to study properties of various materials and then understand its extent to create maybe a prototype of any tiny detail and then present it as a solution for the betterment environmentally and economically? So Noor Bashir, it's a fantastic question. It really is a fantastic question. I'm always struck that when someone says, what do we do with this product at the end of its life? As though the material is going to stop persisting. If I look around at things which are being made right here, and consider something as simple as this, that's got probably 6 different major materials. All of them existed before I did, and they'll all persist long after I'm gone. And what we've done by expending resources and energy to produce this is to, as it were, ossify the energy to make this. So I think that my answer to your question is, you need to think about this through the whole of its life, not just the point of manufacture, the point of service, but at the end of its service. If there's an end of life, it's only the end of its current use, and it will persist long after that. And I think that starts to color your thinking about, well, how do you make decisions in manufacturing? How do you make priorities for being able to recover this at the end of its current service life, so that it can be used for something else? I'm sure you've heard of the circular economy, and perhaps you've heard of the work Cradle to Cradle, which is really trying to think about the whole process of this coming from the ground, being turned into this object, being used as this device for a certain amount of time, and then being reused, if possible, for something else. These things are really difficult to take apart. They're bonded. Lots of the materials are bonded by thermal forces. This will probably end up in a landfill. You might describe this as not very good circular economy design. But the thing with the aluminium and the timber is a better example, where you're trying to think about what happens at the end of their service. So that would really be my advice, is yes, start at the small scale and try and figure out how things fit into the grand scale, the global scale. I hope that answers the question. Next one. would you be able to suggest any resources interested in utilizing generative designs in their workflow? So Jack Traylor Powell's next on the list. Yeah, so generative design is an interesting one. You don't get anything out that you don't put in. So you set the priorities, you decide what's important. And I'd encourage your time at the Bartlett as a really deep dive into deciding what is important. Because the computer's only going to go in the direction you tell it to go. If you say cost is the most important, the computer will marshal all of its computer power to optimize for cost. If you say weight is important, the computer's going to marshal. If you say both are important, it starts to get interesting because you end up with a trade-off. And I think the proposition with generative design is that it's making solutions that are guided by you saying what's important. So be careful what you wish for, because that's the direction that the computer is going to optimize for. If you're interested in resources, so Autodesk have an academy online which teaches certainly for Fusion, for a piece of software for solid modeling, Fusion 360, where you can do generative design inside the modeling environment. That would be one good place to start. But there are lots of other resources too, but that might get you on get you going. Next on the list is Edward Lawrence. How construction could be made similar to other forms of industrialized manufacturing, such as automotive. What do you think has held industrialized construction back from becoming more widely used? Yeah, so the Lustron house. So the Lustron house, if you that way around, if you look at this, so from 1955, couple of things. So building factories is a really large capital cost. And so when you do that, you need to keep feeding the machine. So one of the barriers to adopting industrialized manufacturing in construction is you need to keep the demand. If you could keep making Lustron houses, if the market was alive to the Lustron house, it probably would have sustained itself for longer than it did. But here's the thing, it wasn't a very flexible process. And that's one of the things that automotive, certainly, perhaps aerospace slightly less, but certainly automotive is really good at now. Mass customization is within reach. If you look at, say, Motorola, early 1980s, they could make you a pager. Every single one of the pages could have well over 10,000 different permutations. The reason that you could do it is that there was a very good coupling between being able to market a pager to a customer and the connections all the way down the manufacturing process. The marketeer at the front end knew the degree of flexibility that could be offered all the way down the supply chain at the manufacturing end. Construction's really bad at that. What those two reports, the Latham report and the Egan report, really did is to show that at the customer end, there's very poor reach into the ability of the construction industry to be flexible all the way down the supply chain, because there's so much risk in promising that. So what you get instead is conformity. And that's one of the challenges. I hope that goes some way to answer the question. Next question, what is the approximate cost of these models and facilities and other advanced? Will this be an expensive experiment? Well, that's a really good question. And I think that the reality is that there will need to be some expenditure for things like materials. And this is really something that you'd have have a conversation with your tutors as to what level of expectation that you've got. I think that the fair answer to your question is that if you're curious and you're led by your nose, one of the exciting things about manufacturing is that you can reach out to industry to test what industry offers now, but in the context of an experimentation. So I would encourage, and I think you'll find this amongst all of the academics at the Bartlett, that there is a very keen interest to go to the factory environment, go and visit them, go and talk to them, because they're quite often in a position where they are not doing what they're actually capable of doing. They're doing what the market is currently asking them to do. So I hope this is really trying to turn this into a creative response, that you can create opportunity where organizations may gift you materials that will help you do experimentation. To the best of my knowledge, you'd need to go and speak to the various workshop facilities, either the one at Here East or the one at 22 Gordon Street, to find out exactly what running costs might be for particular consumables like print media or the cost of cutting materials. I hope that answers your question. Rachel, we often look at creating more sustainable materials, but we don't think about wasteful materials that are already present. Is it possible to repurpose materials like plastic and use them in construction? So that's a fantastic question. I'd point out that much as we might talk about new buildings and new technology, in 20 or 30 years' time, because of the rate at which buildings are demolished and areas reused is actually quite small. If you go out in the middle of a city and take a good look around, the chances are that a lot of it will still be standing in 30 years' time. So your question's excellent. What do you do with buildings that get, or how do you repurpose materials which are already, as it were, ossified? That they're very difficult to upcycle as a technical nutrient to new processes, and it's a real challenge. And I think it's one that deserves lots of investigation. Right, next question, Laura Dietzold. In what ways? Oh, that one missed. In what ways can different manufacturing techniques used to be addressed sustainability in construction? So it's an excellent, although it's a general question, but it's a really excellent one. So one of the things that construction always has trouble with is that it's difficult to scale. And again, it comes down to the size of your demand. If you really scale big, you have to have the demand to keep the machine, feeding the machine, basically. But when you scale, you get the economies of scale. And I think that arguably you can reduce impact and you can reduce energy usage if you can find a way of exploiting that scale advantage. But there is a paradox in this. So this is probably not the time to go off on a tangent, but I would suggest that you look up someone called Jevon, Jevon's paradox, which for the economists in the audience, they'll be very familiar with him. He was a researcher that investigated coal production. And he found that as you become more efficient, you don't use less material, you actually use much more. And there's a paradox in that called Jevon's paradox. So although this might not seem to directly answer your question, to be sustainable is really I think, to try to balance your need with availability. And sometimes trying to scale industrial processes just produces more stuff for us, the same amount of capital or the same amount of resource. And I think this is something, just as a word of caution, that this is something that that adopting industrialized manufacturing in construction needs to account for in a really careful way, and it's a balance which is difficult to strike. Yu Chen, how can those technologies be adopted by traditional architectural firms and traditional architectural construction projects? So again, going to that that slide there, I think one of the problems in trying to take advantage of industrialized manufacturing is that you have to let go of some things that are comfortable, that you might call traditional, because if you just try and transfer bricklaying or concrete mixing in a sort of mass scale to a factory, you get almost no advantages. You've got to rethink what industrialized manufacturing already does really well, and not try and basically take the building site and put it underneath a roof, and then you end up incurring the transportation penalty of trying to take these things to site, even if it means in a factory you can make more of them, you know, and take advantage of all of the things you get with a factory. Right, Laura Cadena. How do prototypes in structures comply with building codes and regulations? So this is a really, really interesting question. When you build prototypes, there's always risk. And I would say that part of your time at the Bartlett is to take risks. Part of this presentation has been to take a big risk and think about photolithography as an analog for innovating manufacturing processes, but I did it. And I think that, you know, this is a place where you can really try to test your ideas. I think that getting systems to comply, you can get components to comply with codes, but buildings aren't components, as I hope this talk's tried to get across. It's assemblies of components. And building composites and demonstrating, and some of the things which this presentation tries to show, like, for example, the shutters, does sometimes challenge the nature of the building regulations. And remembering that building regulations, you're trying to achieve a performance, not necessarily a standardized embodiment of that performance. And you may find yourself, when you do this prototyping, to really challenge building regulations and challenge building codes, and you may end up doing it in a really creative way, which questions the assumptions of the code without actually sacrificing performance. I hope that answers your question, Laura. Joshua Schnell, are there opportunities, or better that channels that are already open to MArch Parts 2 students to use the Here East campus, potentially collaborating or learning with those on other courses? I think the question for your tutors. Try and dodge that one. I think a conversation for your tutors. I'm sure that the right kind of proposal would provoke the possibilities of cross-fertilization. I think that design for I think manufacturing full stop is and has historically made a lot of its innovations by basically collaborations that have been across fields in different disciplines, not necessarily by just becoming an expert at one thing. And the reason's quite simple. Most really hard problems have absolutely no respect for arbitrary academic disciplinary boundaries. They're just hard problems. And I think that trying to reach out is definitely the thing to do. All of this is collaborative. You can't do this on your own. Jose Hoyos, the word manufacture comes from made by hand, but nowadays it is reality industrial processes at large scales. How can we move forward in order not to lose that origin? How can we avoid falling into an industrial idea that outgrows our artisanal processes? So this is a very good question. Where is the making hand in this? I have a simple answer. I hope that it, Jose, that it addresses your question. I actually don't think it's lost in doing industrialized manufacturing. I think the artisanal process, if you're talking about the maker's hand being directly evident as a witness mark on the made part. The intellect deployed the hands for the shaping. And in a lot of industrialized manufacture, the intellect merely being projected or even amplified using computers, potentially using machinery. And it's merely one step removed by the machine's witness marks on the final made article. I often get challenged that automatic machines are, you've lost all of the tactile interaction with how the machine operates. But I think that's simply wrong. So a milling machine, a CNC milling machine that has a feed rate or a feed and speed rate, which is cutting a piece of metal in a way which is either producing a very rough finish or potentially inducing oscillations. You don't need to be physically using the machine. You can hear it. You can hear when a feed rate's going too quickly, or when a feed rate sometimes might not be going quickly enough to be cutting a material effectively. So I think a lot of those tactile connections that you have between projection of the intellect, this is what I'd like to make, with the process of making that object on a machine are still there. So I think that connection between the artisanal is merely evolved, just like our needs are. I hope that answers your question, Jose. Clara May, student of architectural computation. I'm very confused the specific direction research at this major. I feel the project you're presenting is more related to building related machinery. So the work that I'm showing are really examples of how manufacturing and in particularly prototyping might be used. They're not, although I teach on the MSc in architectural computation, the world of computation also relates in part to manufacturing, but this talk has really been for the whole of the school and really for the Bartlett community as a whole. It's not specifically for architectural computation. I hope there are others who are listening who aren't necessarily doing the architectural computation course. I hope that answers your question. Harshal, much is done around climatically challenging areas like snow-covered mountains and frozen oceans. We continue construction in such areas and impact is widely known in form of native flora getting affected. Or research done here in the materials of construction practice or proven to have a minimum impact. Okay, Harshal, I'm not exactly sure what the question is. It sounds like it's a question about environmental impact of construction. I'm not an expert in that area, so I might decline to give a specific answer. All I would say is that all materials and all manufacturing processes have some impact, and I think design for a circular economy is not about efficiency. It's about efficacy. It's about balancing available resources and trying to couple them to need and how that need might change over time. I hope that goes some way to answering your question. Next question. Pauline, in addition to searching for solutions for upcycling existing materials, do you think it would be possible and valuable to rethink the design process? In other words, focusing on designing the systems or cycles in which materials may change purposes and forms. My message might be getting across. Thank you, Pauline. Thank you so much. Yes, Pauline. So this is not about formal copying of biological forms. This is about trying to take the processes that biological forms have with their environment and purposing them in the way that buildings might also be organized by the passive flow of energy through them, for example. Our choices of materials could be part of that calculus of resilience. And I think that the design process is inherently four-dimensional at very least, because why should buildings be static when they're constantly being exposed to an environment that's dynamic? it would make much more sense for a building to be variable in its performance in response to the environment that's varying around it. So I think the design process and our design thinking share for sure. It needs to evolve. And I think that the use of manufacturing techniques takes us away from just dealing with static performances and much more tuned to the way that biological systems work. Biological systems, I don't think that they're high efficiency. I think they're high efficacy. They balance a minimal use of resources because energy is expensive. You've got to go out and eat it to convert it from chemical energy into mechanical energy. Materials expensive. You've got to grow it from cell level upwards. For sure, that balance and that change in thinking of the design process, I'd say, Pauline, is like, it's really central. I'm not sure if we're out of time, but I'll try really hard to get these last questions, get some answers to these last couple of questions. Keywords use reuse, rethink, repurpose, and transfer of materials. What about materials recycling? Yes, I think we should recycle, but I think we do much better to think through upcycling the materials that were there to begin with and that we're only a partially temporary custodian of while we use them in a building and then have to use them for something else. And I think we really should be thinking about not what the building is that we're building for, but how the building might be repurposed at the end of its service. And I think that's something which is really challenging. Right, next question. Most robotic fabrication processes happen off-site controlled environments. Do you think having on-site mobile robotic processes can improve productivity and digitization in construction? So as someone who's dabbled in deploying robotics in the field, I would have this to say: the repeatability and reproducibility of dimensional and geometric tolerance by anything mechanized on a building site is something of the order of magnitude worse than trying to do the same thing in a factory. And I think that that alone makes you get cautious about thinking that you should put robots on building sites to replace certainly an operative who's laying bricks. I know it's been done. I know there's a whole initiative with clay printing and polymer printing whole buildings. I know NASA are doing it with the Mars habitat, and many researchers are doing amazing work, doing it with concrete and so on. But the point is that industrialized manufacturing lends itself to efficiencies that you can control in a factory, because you can achieve better dimensional and geometric tolerances of your parts, components, and assemblies. So I think it's not a question of digitization, it's a question of trying to create an environment that's most effective for the manufacturing process that you're trying to deploy. And the crane and other way around, all of the stuff you see on the building site conspires against you. So I hope that answers your question. I think we might have run out of time. So I want to thank Nisat Tasmin very much for being a host, and I'm sure you're all looking forward to the next Bartlett Together event, which I think is tomorrow morning. So I'd like to thank you all for listening. I hope it's been a worthwhile hour, and I hope you feel inspired and energized by some of the ideas that have been presented.